Hi, I'm here with Mike Kilburn at Dees Electric in Manchester Center, and we're going to talk today about geothermal energy. Mike, can you tell us just the basics, the history, and what the heck is geothermal?
Oh, geothermal is actually fairly old technology. We've been doing it since the late 70s, early 80s. It's a process where we extract heat out of the ground and run it through a refrigeration piece of equipment and use that to heat your home.
No, wait. You're taking what I think of as cold water out of the earth and putting it through a refrigeration process. Can you explain that, please?
Sure. It's a lot like taking a glass of water from the sink or tap, and if you have your own well, that's going to come into the house at 47 degrees. And you take that glass of water and put it in your refrigerator and lower the temperature of that water down to 36 or 38 degrees, whatever your refrigerator is set for. The refrigeration system on the refrigerator is absorbing that heat and rejecting it somewhere. And I bet if you feel down near the floor or up near the ceiling, there's warm air coming out of that refrigerator into the room. And that's how it moves the heat from inside the refrigerator to outside. We're doing the same thing on a much larger scale.
And does it get pumped into a forced hot, like what I would call a forced hot water system or something like that?
Yes, it can be forced hot water, but the most of the geothermal work in the United States is forced air. It works really well with radiant heat, so that's another option. But the bulk of the work in this country anyway is forced air on the residential side.
Okay, something I was confused about is I thought geothermal energy created electricity. Does it also do that?
Yeah, that's one of the problems. We're talking about geothermal heat pumps, and there is also a geothermal energy where they drill into the earth where they're close enough to the earth's magma and inject water in there, which produces steam under high pressure, and they use that to turn turbines. Very common in Iceland.
Got it.
So two different technologies using quite often the same name. This map shows underground water temperatures, and you can see the 47 degree line goes through right along the border of New Hampshire, Massachusetts, Vermont. And we're in that zone. The tests that we've run for the last 30 years shows that it's about 48 in the fall and 47 in the spring. So it's a fairly stable temperature source. We're using the earth as our source of heat, as we had mentioned, for the winter. And we could have 15 degrees outside design temperature, but the earth itself is still at 47 or 48 degrees. And our objective here is to extract that heat and move it into the house to keep the house at 70 degrees. And in the summertime, we can reverse that process and take the heat out of the house and reject it back into the earth, where we recover some of that later on in the next heating season. This slide represents how we're extracting the heat. The ground loop will have anywhere from one to a large number of holes where we put in a polyethylene tubing heat exchange system. We're pumping water freeze-proof solution through that loop, and if we get that size properly, so we're getting a decent heat exchange, then it'll, as the water flows out there through that loop, it picks up heat and returns it back into the house. And we're looking at 5-6 degrees of temperature variation there. So it might go out at 40 degrees and come back at 46 to the house or something along those lines. Here we're showing various types of loops and how the loops can be configured. The top left one is a horizontal loop, usually buried between 5 and 7 feet below ground. Top right is a vertical loop, That's the more common one in this area. It involves boring a hole down anywhere from 250 to 400 feet and sinking the geothermal into that hole and then grouting the hole back up. The advantage to that one is it doesn't take up much space. The horizontal one on the top left takes up more surface area, and that can be a problem at some home sites. Left is what's called an open loop. That's where we're using a well in the aquifer, then pumping water out of that aquifer, which will again be at whatever ground temperature is the temperature of the water. We extract 8 to 10 degrees heat out of that and then discharge the water that's been heated. In this case, they're showing it discharged to a pond, but it can go to a dry well or some other system that's sized properly to handle the amount of fluid that you're pumping. The bottom right is what's called a closed loop, but it's in a pond. This is probably the more difficult of all of them to do. It requires quite a large amount of pond surface and also depth. I think we need probably at least 10 feet of depth. And that pond has to freeze over in the wintertime or it won't work. So it needs a layer of ice to make it function properly. And here's a slide that demonstrates where the efficiency is coming from. On the top left, you'll see we're putting in 1 kilowatt of energy into this system and using that energy to move heat from one location to another. We're moving heat from the ground into the house, and we can extract 3 to 5 kilowatt hours of energy depending upon the system and where it's located and what our design is. And you end up putting in somewhere between 4 and 6 kilowatts energy into the house. So worst case on this slide, you're getting 4 and paying for 1. If you lived in a little further south, you could approach the 6 number and you could get 6 and put in 1 in terms of your efficiency. So that means that if we're getting 4 for every 1 we put in, we're 400% efficient. This chart was done December 2011, and the average cost for fuel oil in the state per million BTUs was $34.22. The average cost for propane was $44.32. Electricity was $43.96 per million BTUs. Not much difference from the propane. However, if we use that same electricity at $43.96 and run it through a geothermal unit that's getting a COP of 3, then it's like paying $14.65 per million BTUs for your heat, which is very close to what you'd pay if you were cutting green wood at $14.39. So it becomes a very cost-effective heating system.
Mike, can you tell me what the upfront cost might be on a new home?
Yeah, geothermal has a higher upfront cost. The home that we're visiting, the geothermal was in the $15,000 to $16,000 for the equipment and getting it connected to the loop. The ductwork, I think, was in the $8,000 range, and I believe the cost to get the vertical holes bored in and excavated and into the house ended up being in the $5,000 range.
Okay. There's a house across the street we're going to go look at it was just constructed, and it has geothermal heat. Is that what you call it? Mm-hmm. Okay.
Geothermal heating system.
Okay. And we're going to go look at it. So let's take a look at that now.
This is a typical forced air geothermal system. It happens to be a dual capacity one. The copper piping to the right is a hot water assist feature that this unit has, and whenever there is extra capacity available, we're taking a little bit of that capacity and heating their domestic hot water. I think here at Frank's house, they're probably going to get somewhere between 50 and 60% of their hot water off of this unit. The lower set of pipes that you see that are black there, that's the connection to the ground loop. It goes in to the Geo unit at that point, and we extract some heat out of that fluid and pump it back out to the loop. Inside this cabinet, there's a compressor on the bottom side. That's what you're hearing running right now. And in the upper portion of it is the fan and heat exchanger that's moving the air through the house and discharging that heat that we extracted into the house air. It gets filtered with a MERV 11 filter and then gets returned back to the house. Fairly straightforward, simple ductwork air delivery system.